Hello and welcome everyone. So in this video I'm going to talk about these three exercises. And let me zoom in on this one as I'm talking because this one maybe is a little bit more difficult to see the way that I've got it. Alright, so these three exercises I had placed on the board as sort of a participation check or sort of a progress check going out of the choice lecture and then kind of approaching the first exam in intermediate micro. Right, so after having gone through the choice lecture, think about where that falls relative to the course and variant, right? It's like budget constraints, preferences, utility, then choice, then demand. After having gone through the choice lecture, we covered like how do you solve the utility maximization problem for each of our four quintessential utility functions, right? Perfect substitutes, complements, Cobb-Douglas, quasi-linear, right? After going through those examples, and after going through hopefully the intermediate micro exercises, like here I call them IMX 1, right, for exam 1. After having gone through those exercises, having gone through the lecture, those examples, these here should be relatively easy, right? You want these to be easy, to be able to approach the first exam in intermediate micro with confidence. If they're not easy for you at this point, if you're just not there yet, that's okay. We'll kind of get there as a result of this video. So what I'm going to do is I'll talk about each of these. I'll read through them. I'll kind of tell you what the setup for the problem is. Then I'll give some thoughts just from the slide. Then I'll show you the solution I wrote out on the board. Then I'll give you my full solution. And that way, so go through the video, you'll be able to have the guidance that you would need to be able to get yourself back on track if you had done something wrong without like losing the whole value of working through the exercises and just seeing the solution. If you just want to skip to the end, then yeah, you can see the solution. And so I'll try to remember to make that like the very last thing in the video too, just to have like the solution at the end. But after I explain it kind of thoroughly in the middle. All right, if you like the video, please let YouTube know that you like the video, right? Click the like or leave a comment or something like that. That's all really important for the algorithm, which matters to me in the sense of like, the whole reason why I have this channel is because I want to help as many people learn economics, in particular intermediate micro, and then microeconomics as possible, because I myself benefited tremendously from videos from like another professor 20 years ago, right? So 20 years ago, I was taking a linear algebra course, and I had to self-study, and I was able to learn and benefit from the textbook author, Gilbert Strang, who's at MIT, who had recorded lectures from the previous, I guess it must have been the previous spring, right? So spring 2002, and then I self-studied like going into the summer term, right? And it was super important for me, super useful, and that's my inspiration for doing this now. Okay, so enough of that, but what I want to do is kind of talk about what each of these exercises are doing. So this one is utility function, where utility is coming from x plus 3y, right? Prices are 2 for x, 3 for y. Income is 24. You just want to find the optimal bundle. This is the consumer's utility maximization problem. For the second one, utility is coming from whichever is the smaller of x and y. Price of good x, I wrote it as 1 here. Price of good x is 3. Price of good y, I know, I wrote it as 2, but fine, it's just y, right? So price of y is 2. Price of x is 3. Income is 10, right? And so you want to find the optimal bundle. And then for this last one, this one is utility coming from the product of x to the 4th times y to the 3/4. And this doesn't show up super well. This is fraction. It's 1/4. I don't know. Maybe I could have written this as like 0.25 and then 0.75. You'll see some authors doing that. I don't like that because I think the decimal point, especially in a superscript, kind of get lost. But anyway, the price of good x was 1. Yeah, I wrote it as good 1 again. Price of good 2, price of y was just 1, right? They're both 1. Income is 16. And I want to find the optimal bundle. All right, so you could pause the video, then you don't have to listen to me. Maybe you've been working them all along or whatever. But, try to work through these three exercises. Like I said, these should be relatively easy by this point. If not, well, that's kind of the goal of the video, right? So, or making sure that they are easy is actually the goal of the video. All right, so first thing I want to do is kind of walk through my thoughts just from what's on the board here, and then I'll give the actual solution. Right, so this first one's a perfect substitutes one, right? So it's perfect substitutes. Remember how you solve a perfect substitutes problem? Well, we have one of three situations that can happen. Either the indifference curves are steeper than the budget constraint, and that's an all x solution. We call that our Alex solution. Or the indifference curves are flatter than the budget constraint, right? The slope of them is flatter than the budget constraint, and then it's our alley solution, our all y solution. Or the budget constraint and the indifference curves have the same slope, and then you get a continuum of solutions along the budget constraint. And the reason why that makes sense, and why all these make sense, is because the goal is you're trying to find the bundle in the budget constraint that crosses the most desirable indifference curve, right? So you want to find the highest affordable indifference curve, right? And so that's why we can kind of compare the slopes in the case of perfect substitutes, and then find whether you have a corner solution, either all x, all y, or if you have like an interior, well, you have like the budget constraint solution. All right, this one right here, this is complements, right? And remember the way that we solve this one is we replace this comma with an equal sign, and we get the line through the origin that connects the corners of these indifference curves. In this case, it's going to be the 45-degree line, the line y equals x. The reason why that works is because, once again, you're trying to find the highest attainable indifference curve. It's going to be the corner. It's going to cross the budget constraint at that one single point. You can't use calculus because this is a true corner. It's a right angle, so you won't be able to take a derivative there. However, we have a system of equations that we can solve for that intersection. So we solve by substitution, and that's what we'll do. All right, this one here is Cobb-Douglas. Look, you should solve the Cobb-Douglas one using the Lagrangian. No, that's not the only way to solve Cobb-Douglas. Yeah, you could just take the MRS, set it equal to the price ratio, and you will get that as a result of doing the Lagrangian correctly anyway. However, it's important to know the Lagrangian approach, and it's a powerful tool that economists needs to have. And Cobb-Douglas is a really good place to do it, right? And so that's the way that I'm going to solve it. But yeah, there's basically, this is going to give us an interior solution. There's going to be a tangency. And so you should know that that's part of the structure of the problem, right? All right, so now let's go over these, right? So go over this a little bit more carefully. Now I'll give a little bit more details. So actually, for this one, we want to think about, let's find the MRS, right? Remember, the MRS, marginal rate of substitution, the slope of the indifference curve, is going to be the ratio of the marginal utility of x to the marginal utility of y. So the marginal utility of x is just the partial derivative with respect to x. In this case, it's 1 because the coefficient on x is 1. The marginal utility of y is 3. So the MRS is going to be 1 divided by 3, or 1/3. The price ratio, it's just right here. I always write like px over py, so I could just like put that line right there, or just like visualize, oh, the slope of the budget constraint is 2/3, right? And yeah, I just said like slope is 1/3 and slope is 2/3, and yeah, these are downward sloping lines, so they have a negative slope. But the thing is, we can report these in absolute value, and as long as we don't give an opposite sign to the MRS and to the budget constraint, it's not going to matter. To the price ratio, it's not going to matter, as long as they have the same sign. Because they're either both positive, because you're working in absolute value, and then we're fine, or they're both negative, and then the sign cancels, right? The idea is they both are going to have the same signed slope, and ultimately, we want to compare the magnitudes. Why? Because we want to know, do we have steeper, do we have flatter indifference curves relative to the budget constraint? Right? Remember what Varian said about minus signs also, which is like oftentimes, look, we know we're working with downward sloping lines here. And same thing, we know the MRS is always negative and the price ratio is always negative, right? And so we just oftentimes will report these in absolute value. And so, like I said, the sooner that you become okay with that, the better for your intermediate microeducation. All right, so we're going to have a budget constraint with a slope of 2/3, indifference curve with a slope of 1/3. So we have flatter indifference curves, right? That's going to give us our all y, or our alley solution. We're going to exhaust our budget on y, right? So y star is going to be how much? Well, the income is 24, so you have to divide the income by the price. That'll give us 8. That'll be the bundle for y. And then for x, it'll just be 0. All right, so next thing we've got to do is we've got to solve perfect complements, right? So we're going to get we replace this comma with an equal sign. It's going to be the line y equals x. Our budget constraint is going to be what? 3x plus 2y equals 10. But I can replace y and x, right? So it's going to be 3x plus 2x is equal to 10, or 5x is equal to 10 or x is equal to 2, right? And then y is going to be, well, y is equal to x. All right, so this one right here, now this one's a little bit more involved. We got to write out our Lagrangian, right? So it's going to be what, L of x of lambda, right, equals the objective minus lambda times the constraint, right? Take the partial with respect to x, partial with respect to y. I took a monotone transformation here, right? So I think about this as 1/4 natural log of x plus 3/4 natural log of y, because those partial derivatives are way easier to take, right? All right, so here's the board solution, kind of reinforcing what I'm saying here, right? So here would be the picture you'd want to draw, right? When you have a perfect substitutes problem, you always want to think in terms of the picture. So you either have this picture where you have the solution on the y-axis, or you have the opposite where the indifference curves are really steep and you have the solution down here, or maybe you have a continuum of solutions, right? So here was the MRS. It was like 1/3, right? Because the marginal utility of x was 1, marginal utility of y was 3. Here's the price ratio, 2 divided by 3. That's px over py, right? 2/3 is bigger than 1/3, so yeah, this is our all y solution. Divide income by the price, and there was our 8y, right? All right, so here's our perfect complements now. So we had x equals y for our substitution. Let's just replace y with x. Then I'll have 3x plus 2x is 10, or 5x is 10, or x is 2, but then y is also 2, because x is equal to y. And then here's the Cobb-Douglas Lagrangian one. Well, so let's see. I guess, so I took my monotone transformation, and I checked something else up here. I took my monotone transformation. So that is, take the natural log of our utility function. So it's going to be 1/4 natural log of x plus 3/4 natural log of y minus lambda times the budget constraint, right? X plus y plus, or x plus y minus 16. Depending on your author, I think Perloff does this sign differently and would have a plus lambda, and then it would be maybe 16 minus x minus y. I have to remember, Perloff, I think, has a plus lambda, but then maybe they just distribute the sign, essentially, is the better way to just describe it. Mathematically, it's the same, right? It's just algebra. Just like, do we want to subtract or do we want to add here? And then that governs whether we add or subtract here and then here. Okay. Anyway, so, and then there, if we distribute the negative. All right, so anyway, so the marginal utility of x is going to be 1/4, 1 over x, because the derivative of the natural log of x is just 1 over x. So it's going to be 1 over 4x, basically. Derivative, or the partial derivative with respect to y is going to be 3/4 times 1 over y, right? That's marginal utility of y. And the MRS is going to be the marginal utility of x divided by the marginal utility of y. Well, if you have a fraction divided by another fraction, that's the same as that first fraction times the reciprocal of the second fraction, which will bring 4y into the numerator. The 4's cancel, so you'll have what? Y over 3x, right? And then we'll set this equal to our price ratio, which is 1 over 1, right? Remember, with our price ratio, that's going to be px over py, right? Solving, we find tangency, and this is happening where y is equal to 3x. So what we're going to do is we're going to replace this into our budget constraint and then go ahead and solve, right? So, well, our budget constraint was just like, what, x plus y. So now it's going to be, what, x plus 3x, or 4x is equal to 16, or x is 4. If x is 4 and 3x is y, then y is 12, right? Okay, so that's where that solution came from. All right, so now let me go over like the full version. Yeah, this is just like the generic LaTeX, right? All right, so here's 3 relatively basic utility maximization problems that you need to be comfortable with for the first exam in consumer theory. That's these right here. So here's how I'd write it up a little bit closer to an exam question. Find the optimal bundle, x star, y star, for consumer with preferences, x plus 3y, facing these prices. Find the optimal bundle for consumer with these preferences, with these prices and this income. And then find the optimal bundle for consumer with these preferences. Okay, cool. So here's the write-up for each of these, though. In the first one, quickest way to solve number 1 is to first observe the marginal rate of substitution is equal to 1/3 because MUX equals 1, MUY is equal to 3. MRS is just the ratio of the two. Compared to the price ratio, which is 2/3, PX over PY. Since the MRS is smaller, we know the consumer seeks more of the Y good. If you sketch the indifference curves, you'll see the highest affordable indifference curve crosses the budget constraint at its vertical intercept. It's our all Y solution, our alley solution. Hence, optimal X is 0, and then Y is going to be 24 over 3, which is 8. Alternatively, we could use your bang for your buck principle. You could compare the ratio of the marginal utility of X to the price of X versus the marginal utility of Y to the price of Y. If you do that, it's going to be marginal utility of X was 1, marginal utility of Y was 3, price of X was 1, price of Y was 3, so it'll be 1 is greater than 1/2. Arrive at the same conclusion, right? Because the marginal utility of Y divided by the price of Y is greater than the marginal utility of X divided by the price of X, we should increase our consumption of Y. And with perfect substitutes, this would always be true. So like our consumer would want to like unboundedly consume Y, but they can't because we're run into the problem where, income is finite. So that's why we get our corner solution. All right, find the optimal bundle for perfect complements. Best thing to do is replace the comma with an equal sign. Find the line Y equals X corresponding to the ray through the origin that collects all the corners of the indifference curves. Highest attainable indifference curve crosses the budget constraint at its corner. Solved by substitution, right? That's exactly what we talked about. And then lastly, Lagrangian method, right? I'll take the monotone transformation first. So the monotone transformation, take the natural log of this thing. So when you take the natural log, right, the exponent comes down out front like this, and then the log of the product is the sum of logs, right? So the log of the product, x times y, is a sum of logs. So it's going to be 1/4 ln x plus 3/4 natural log of x, right? All right, here's the objective function is this part, the constraint is this part. Our general approach to optimization is optimize, either maximize or minimize the objective, and then ultimately substitute in your tangency condition into the constraint, right? All right, so here's the partial with respect to x, here's the partial with respect to y, here's the partial with respect to lambda. Solve the system of equations basically, and that gives us our solution. X star is 4 and y star is 12. Okay, I'm going to go ahead and conclude here. But again, I think I promised I was going to, the very end of the video, it's going to show the solution if you want to just skip all the way to the end. So that is this right here. Or if you want to back up 15 seconds, then you can see the solution in the LaTeX version. Anyway, I hope you enjoyed the video, like the video, and then I'll see you next time. Good luck on the exam.